sac129 number 2. We're given a wave equation for a specific case, and we're asked for the wavelength of the wave in part A. Let's go ahead and find that. What we can do is take a look at the generic equation for a wave from your formula sheet and identify some of the pieces. We're actually asked for a lot of things here. I'll go ahead and identify a bunch of them. So we've got the y corresponding to the y. This is the displacement of the particle along the length of the wave medium from its equilibrium position. Now we've got the amplitude, referred to as y max over here. In the given equation, it's 0.28 meters. A little bit too far with that line. Then the thing that's multiplying the x in the argument of the cosine. The argument of the cosine is this piece right here, the thing that you're taking the cosine of. The thing multiplying the x, the position variable, in the argument of the cosine is 2 pi over lambda. And in our specific equation, it's 7 radians per meter. So 2 pi over lambda is going to be 7 radians per meter. And then we get the minus sign, and the thing that's multiplying the time variable is 2 pi over the period. So 58 radians per second has got to be 2 pi over the period. Alright, so for part A, they want the wavelength. We'll use this relationship right here, the fact that 2 pi over lambda is equal to 7.0 radians per meter. Solve that for lambda. I'll multiply both sides by lambda, divide both sides by the 7 radians per meter, and then switch sides. So I've got lambda is 2 pi over the 7.0 radians per meter. Substitute that into a calculator. I get lambda is 0.8976 meters to too many sig figs. I'll round it off. Everything's given to 2 sig figs here, so I'll round it off to 2 sig figs. That rounds to 0.90 meters. I'll make it more clear that that's a 6 rather than a c for centimeters, and it's actually 0.8976 meters. So it rounds to 0.90 meters. Okay, in part B, we're asked for the period of the wave. The period is represented by the symbol capital T, so we'll use this relationship between our generic equation for the wave, our generic wave equation, and the equation for the wave at hand. And I've got 2 pi over t then, so it's multiplying the t, so 2 pi over t has got to be equal to the 58 radians per second. So 2 pi over t is 58 radians per second, or t is 2 pi over 58 radians per second. Plug the values into the calculator. Should recognize over here I get, you can think of it as meters per radian, or this 2 pi that appears in this argument here actually has units seldom written. Remember, the radian is not a standard unit, but rather a fraction of a circle, so we can take it out and put it in as we want. But you can actually think of this as 2 pi radians in this whole argument here. Same thing here. Or we could look at it as units come out seconds per radian, and we just get rid of the radians in that. It's not, the one thing that's not a true unit that we see in physics. At any rate, t turns out to be 0.108 seconds to too many sig figs, so round that off to 0.11 seconds to 2 sig figs. Alright, next I want to know the frequency of the wave. The frequency given on your formula sheet as 1 over t right here. And we'll go ahead and use that. So part B, sorry, we're up to C. You got frequency is equal to 1 over t. I'll use my intermediate result to get an accurate value for the frequency, and then round the result to the 2 sig figs. So this is 9.26 1/2 which is hertz, which rounds to 9.3 hertz. So F is equal to 9.3 hertz. Then in part D, they want to know what's the wave speed. The wave speed is the wavelength divided by the period. Let's see if we can find that on your formula sheet. Right here. Distance that it travels in a period divided by a period. So wave speed is equal to lambda over t. Again, I'll use the intermediate results and then round off to the proper number of sig figs later. So way too many sig figs there, well, too many, and then divided by the 0.108 seconds, and I'm getting 8.31 meters per second for the velocity, or this often means approximately equal to, rounded to 2 sig figs, we get 8.3 meters per second. To 2 sig figs, as were all the given values. Okay, next, part E. They want us to find what? What's the tension in the string? Okay, so we've got a wave and a string, and we've been able to get the wavelength, the frequency, the period. The tension in the string, remember, the tighter it is, the greater the frequency. Let's see if we can find that relationship between, yeah, it's actually the greater the wave velocity, so greater the frequency for a fixed wavelength, but in general, the greater the wave velocity. So the wave velocity is determined by the tension. That F sub t is the tension, and mu is the linear mass density, that mass per unit length. So let's see if I can remember that equation long enough to copy it over here. We've got V is equal to F sub t over mu. And we're supposed to be solving for F sub t. We do have a value for V. I use this intermediate result in the calculation. I'm going to need mu, the linear mass density, and that's given in the problem. The string has a linear mass density of 0.0032 kilograms per meter. So every meter of that string would have a mass of 0.0032 kilograms. So mu and V are known. I'm going to solve for F sub t. I'll start by squaring both sides. And then multiply both sides by mu and switch sides. So F sub t is just mu times V squared. And I can go ahead and substitute the values with units. I'll move up here for part E. F sub t is 0.00, and now I forgot the value, 32 kilograms per meter times the 8.3 meters per second squared. So F sub t is 0.0266 newtons, which to 2 sig figs. I guess I actually wanted to use the intermediate result. I said I was going to use that result. And in fact, when I plugged it into the calculator, I was using that result. So the tension in the string has got to be 0.027 newtons. In this case, and then this last part of this problem is part F. What's the amplitude of the wave? The amplitude of the wave is, of course, the y max. By inspection, the amplitude of the wave is 0.28 meters. And that should wrap it up, except for the fact that this value actually, this expression up here actually evaluates to 0.022098, which rounds to 0.022 newtons. All right.